All right, welcome everyone to today's AI/ML seminar. I'm pretty excited to have Rob, giving the talk today. He's a fourth-year PhD candidate working with me and Parik Smith. Over the course of last couple of years, he's been working at the intersection of language and structured knowledge, specifically looking at ways to find out if language models know knowledge or not, and if not, to try and inject knowledge into them. And today he's going to be talking about some of the really exciting work he's done recently. But throughout his last couple of years, he's collaborated with people like at places at AI2, Google, and DiffBot. And he's also been awarded the Noyce Fellowship and the Rose Hills Scholarship as well. So yeah, pretty excited to have Rob. Rob, take it away.
All right, thanks for the introduction, Samir. Can I just quickly check that everyone can hear me? Can someone give me a thumbs up? Okay, cool. All right, cool. So today I'm excited to talk about some of my recent and ongoing work investigating applications of what we've been calling prompts to problems in natural language processing. And before I get started, I'd like to motivate this by just going over one of the major developments in NLP over the last 3 years. So in natural language processing, our problems tend to look something like this, where we have input that's in natural language, and we want to predict some kind of output. So here we've got a pretty straightforward sequence classification problem. And so you might say that if the input's once upon a time, you might want to predict that the output is something like fairy tale as opposed to news article or like academic paper. And so if someone wanted you to solve this problem 3 years ago, you might adopt the following approach. You would take this text input and you would break it up into what we call tokens. So these might just be each word in the text, or they might be, fractions of words. But typically at this point in time, people would look at individual words. And then for each of these words, you would associate an embedding. So these things are usually learned during training, but they could also be pre-trained using a model like Glove or Word2Vec. The details aren't too important. And then you would take these embeddings and feed them into your favorite sequence encoding neural network. So the popular option at the time was LSTMs or bi-LSTMs. And this would give you out a sequence of vectors that are now not only representing the words, but incorporating some global information from the sequence. So now if we want to get this to predict over a categorical distribution, we then need to map this sequence encoding down into a single vector. So one of the popular options for LSTMs is just to use the last vector from the encoding. You could also maybe average these together or take a weighted average using a attention mechanism. The details of that aren't that important either. The point is that once you get this single vector representation of the sequence, you'd apply a linear projection, and this would give you your logits over your target categorical distribution. So in NLP, when we have architectures like this, it's become a pretty common trend to evaluate them using a benchmark that's comprised of a lot of data sets. So the popular one at the time is the GLUE benchmark, which includes a bunch of natural language understanding tasks. And just to highlight sort of what's here, this COLA data set, you're given a sentence, and basically you have to predict whether or not it's grammatical. SST2 lets you predict, given a review-like text, whether or not the review has a positive or negative sentiment. And basically the rest of these data sets test similarly fundamental linguistic capabilities. So then that is a summary of what 3 years ago in NLP looked like. And now let's move forward 1 year. So if you didn't catch the change in the last slides, the only thing that we've really switched out is we've taken our LSTM and bi-LSTM and switched it with ELMO. And so to quickly explain what ELMO is, it's actually fundamentally the same model as an LSTM, or I should have bi-LSTM written here. But we've added this additional step that we call language model pretraining, where basically we use a language modeling objective to train the model weights, and then we transfer it to a downstream task. And so what does a language modeling objective look like? Essentially, what you have is you have a piece of text, and then you want to predict how to complete the sentence. So given this context, we have a categorical distribution over our entire vocabulary. And the idea is if we have a large corpus of text, we can then train this model to predict the observed tokens in this text. So the goal of language modeling is really just to predict the next word. The nice thing about this objective is that there's lots of cheap supervision for it. Essentially, any piece of text you find can be used to train this model. And so you can train a language model on all of Wikipedia or all of GigaWord. You know, there's terabytes and terabytes of text out there that you can use to self-supervise these models before you transfer them to downstream tasks. And just to quickly clarify the terminology that's typically used in NLP, we'd refer to this language modeling self-supervision stage as pre-training, and then training the model on the actual task of interest as fine-tuning. So if I use those words, that's what I'm referring to. Okay, so if we take the Elmo model and compare its performance on GLUE to a randomly initialized bi-LSTM, we see a pretty stark jump in terms of the score uniformly across all tasks. And this caused quite a stir at the time because in NLP, people had been kind of fighting over maybe 1 to 2 point gains for all of these kinds of tasks. And then suddenly by just using this language modeling objective, which language models have been around since the dawn of NLP for the most part, you were able to get a jump from, like on average, from 63% averaged accuracy across these tasks to like 70. So this was massive. Okay, and then just to quickly catch us up to the sort of modern era of NLP, I'll call it. Again, we can see that we've really just switched out the neural network. Instead of Elmo, we're using BERT. I'll also note that now it's pretty common that people will use what are called word pieces in the input instead of full words. So instead, you can see that the word upon can get split into something like the prefix up, and then this hashtag lets you know that you're continuing the word so that you have on. And this is kind of nice because it allows you to have a much more flexible vocabulary using much fewer amounts of tokens. Okay, and so to quickly explain what BERT is compared to Elmo, basically if you take this LSTM and you switch it out for a more modern architecture called the transformer, which I won't go into the details of what it is, but essentially it's just much more scalable for training than an LSTM. And then you take your language model pre-training and switch it out for masked language modeling pre-training. This essentially gets you BERT. There's a couple details I'm skipping over, but this is the essence of what BERT is. And so what's the difference between language model pre-training and masked language model pre-training? Essentially, instead of doing this complete the sentence style task for language model pre-training, we instead take a full piece of text and we mask out some of the words and then train the language model to instead fill in the blank. So masked language models essentially can see context from both sides of the prediction instead of just what came before. Okay, and so in essence, that's what BERT is. There's a lot of follow-up BERT-like models, but the essence of what these models do is pretty much fundamentally the same. So again, if we look at performance on the GLUE benchmark, we again see this like massive jump in overall performance where we've now gone from 63% with a bi-LSTM to 80% accuracy using BERT. And for some of the tasks, the jump is just extremely dramatic. So just to highlight COLA, we've really like trebled the performance. So yeah, the whole point of this introduction is just to establish some terminology and also establish that pre-trained language models are extremely effective at transferring to downstream tasks and accordingly have become an essential component of pretty much any modern NLP pipeline. And so because of this, it's become a very important question in NLP to understand what exactly these models are learning during pre-training that makes them so successful at transferring to these downstream tasks. So we're really interested in understanding, is this language modeling objective teaching us factual knowledge? Is it teaching us linguistic knowledge? So on and so forth. And so now moving on to the crux of the talk, I'm going to talk about a technique called prompting, which we've initially used to diagnose the knowledge of language models. Okay, so the idea behind prompts is pretty simple. If you want to measure a language model's knowledge and you have a task that requires that knowledge, then the key idea behind prompts is to take instances from that task and reformulate them as language modeling problems. So to provide a concrete example, if we're looking at sentiment analysis, here is a standard input and label from the SST2 data set. So your input might be something like the acting in this movie was phenomenal, and the associated label would be positive as opposed to negative. So how do we turn this into a language modeling task? Well, basically what we need to do is take the input, and then we can add some tokens to sort of set this up as a complete the sentence or fill in the blanks problem. And then the last step is that we take the original task labels and we map them to words in the model's vocabulary. So if you wanted to do sentiment analysis, you might take your input, then say, overall, this movie was, and see whether the model predicts a higher probability for the word good versus the word bad. And so you can imagine that you can do this across all of the instances in a data set like SST2. And if the model is overall getting most of the instances correct as opposed to incorrect, this indicates that the model has learned essentially something about sentiment. Okay, so there's a number of benefits of this approach. I would say first and foremost, it's nice because it studies language models' behavior in sort of their natural habitat. You're really using natural language as an input and an output. And so in contrast to other methods that people have used for diagnosing language modeling knowledge, it's really not making any modifications to the model or trying to study patterns in the model's weights or internals that might be spuriously correlated with a phenomenon of interest. The other thing that is nice about this prompting-based approach is that it provides a lower bound on what a language model knows, in the sense that if you can create a prompt that's able to consistently get the language model to output correct predictions, that's a pretty good indication that the model knows how to solve the task. But if you're not able to create a prompt that gets good performance on a given task, that doesn't necessarily mean that the language model doesn't know how to solve the task. It could be that your prompt is just not working well. And we'll study later how we can try to fix that issue if it occurs. Okay, so just to rigorously sort of define what the elements of a prompt are, we essentially have for any task a number of task-specific input fields. So here I'm going to look at the task of paraphrase detection, where you have two sentences instead of just one sentence. And I'm just doing this to illustrate sort of how flexible prompts can be. So for paraphrase detection, we have two sentences, and then we want to predict a label 0 if they are different, or 1 if they are similar or identical. So now the next element of creating prompts is to define this label token mapping. So as we can see, 0 and 1 don't really have they have an intuitive meaning, but the labels don't really represent that intuitive meaning. And so we have to manually define how these labels get mapped into the vocabulary in order to have a better chance of in order to give the language model a better chance of filling in the blank properly. And then the last element of a prompt is this template, which defines where the task-specific input field should go, as well as the blank that we want to fill in. And then we also have these prompt tokens in black, which we manually define and are shared across all of the instances. And so if we take these things and mix them all together, this gives us our prompt. So as you can see, there's one prompt really associated to each instance in a data set. And so then given this prompt, we can then feed it through BERT, and we can measure its probability over our label tokens. And then to map this back to the classes, we essentially just marginalize over those label categories to get the original label probabilities. Okay, so let's see a couple of cases where we've used prompts in action. So in my research career, the first time I needed to use these was on a project, a paper that we had titled Barack's Wife Hillary, where essentially we had noticed this phenomenon that language models did quite a poor job at completing factual sentences. And so what we wanted to do was create a model that was able to address this problem by sourcing extra information from knowledge bases. And so we had used these prompts just to illustrate that the model was able to fill in sentences that were based on facts in the knowledge base correctly. So kind of this work was done before language models had really been popularized in NLP, but we had published it concurrently with this GPT-2 paper, which, if you might remember, was pretty notable at the time because OpenAI had shown that it was able to generate all this beautiful text and had sort of notoriously concluded that it was too dangerous to release to the public. But they did release a smaller version of the model. And so here we can see how our model competes with GPT-2 at filling in these fact-based sentences. So we did this for 6 different types of facts that were available in our knowledge base, and we can look at aggregate results. And sort of a great victory at the time for us was that we were able to show that in most cases, the model is able to do much better than GPT-2. And another model called an AWD-LSTM, which was architecturally similar to our model, but didn't have the knowledge sourcing component. And just to explain the metric here, hits at 1 is basically measuring whether or not the correct token to complete the sentence is in the top 1 predictions of the language model, and hits at 5 is a similar construction, but for the top 5 predictions. So this was a big victory for us because our KGLM essentially was using an order of magnitude less parameters and was trained on, I think, like 2 orders of magnitude less training data. So this was showing this did a very great job showing that our knowledge sourcing component was very helpful for fact-aware language modeling. So subsequent work on this task has pretty much used this technique of prompting as a mainstay for evaluating these models. So after Barack's wife, Hillary, I worked on a follow-up paper called Knowledge Enhanced Contextualized Word Representations, where instead of improving a typical language model, we used a similar approach to improved masked language models. And we're able to show that this performed much better than BERT. Concurrently with this work, there was also a paper published called Language Models as Knowledge Bases, which created a data set called Llama, which has now become a standard benchmark for evaluating fact awareness of language models. This prompting technique has not only been used for studying fact awareness, but it's also been used for studying other capabilities of language models. So there's this Blimp paper that came out of Sam Bowman's group, where they've established a similar data set to Llama, but it tests whether or not language models have knowledge of linguistic phenomena. And then sort of famously in the GPT-2 and GPT-3 papers, they also showed some pretty astounding capabilities of their massive language models. So in GPT-2, they were able to take a long body of text and then show that if you appended the string TLDR to the end of it and then generated from GPT-2, it actually had pretty good text summarization capabilities. And similarly for GPT-3, if you have these extremely large language models, you can basically take a task and formulate it in text, and the model generally does a pretty good job solving this task. So this is like a 0 or a few-shot setting, since you can only add a description of the task or just a few examples illustrating how to solve it. So while prompting is pretty useful, it suffers from one major pitfall, which is that writing good prompts is really more of an art than a science. So it requires a lot of experimentation, manual effort, and intuition as to what the language model is going to do given a certain type of input. And furthermore, this is problematic because it's not always obvious how to pose a task as a language modeling problem. I've stuck with things that are pretty easy, like sentiment analysis or completing very straightforward facts, but there are more complicated tasks in NLP, such as natural language inference, where you're trying to detect whether 2 sentences are contradicting each other, essentially. And that's a lot harder to pose as a problem using prompts. So to address this, we developed a method called autoprompt, and this was published in the latest EMNLP. And so our question was, can we automate prompt construction by providing some kind of supervised training data when we're trying to train the prompts. And so to quickly jump to the answer, we found that the answer is yes, but your prompts might start to look something like this. So looking again at the task of sentiment analysis, instead of asking whether this movie was good or bad, according to auto prompt, you should be asking whether rating nomination, partnership, or unconstitutional. And so the point is that the prompts may work, but they may not make sense to humans. And before we see how well they work, I'd like to just quickly go over how we learn these prompts. So going back to the anatomy of a prompt, if we look at these different elements, we can highlight the ones that require manual effort. So there's really two. The first is defining this label token mapping, and the second is picking the prompt tokens in this template. So first, let me go over how we figure out label tokens for our tasks. So our approach was pretty simple, and it's kind of heuristic. The idea is that if we take these inputs to BERT, we can keep BERT frozen and then have it fill in the blank. But instead of projecting into the model vocabulary, we instead learn a linear mapping into the label vocabulary. So this is just a linear projection on top of the model, and this gives you the logits for each label. So one thing that's nice about linear projections is that you can interpret each row in the projection matrix as an embedding of these labels. And so the key idea that we had was, since the BERT model is frozen, if we take the label embeddings and then look at the output word embeddings from the vocabulary projection matrix, we can essentially associate the top k nearest neighbors from the vocabulary matrix with their associated labels that we learned from our learned projection matrix. And so if we do that, now we can get automatically label token mapping. So instead of looking like this, they start to look something like this. All right, so now moving on to the problem of figuring out the template, our key idea here was basically instead of manually writing some prompt tokens, we instead can manually define where placeholders go. And so here I'm showing you what the placeholders might look like if we were trying to generate this movie was as a template. You can space them arbitrarily though. So here we've got these T placeholders that are showing you where we want to fill in prompt tokens. And then to learn the prompt tokens, we used an approach that was previously published called universal adversarial triggers. This was developed by Eric Wallace when he was an intern at AI2 and studying at UCI. And the key idea behind this is that you can find pieces of text that you can append to the front of model inputs in order to provoke the model to fail or to have language models produce sort of racist or wildly offensive language. And so in this work, we decided to repurpose this adversarial triggers approach for good instead of bad. And so using the same approach, we wanted to train it in order to increase the probability of the labels conditioned on the prompt. And so now I'll provide a brief description of how this universal adversarial triggers method works. Essentially, for each of the template slots, for each of the placeholders that we had previously defined, we're going to randomly initialize some candidate prompt tokens, or we're going to just initialize them all to masks, which is what we did in this paper. So then with these prompt tokens, we can then instantiate the prompts for a batch of examples and measure the probability of the labels under the prompt. And so that's illustrated in this matrix to the right. So then what we can do is we can measure the gradient of the loss, the gradient of the label likelihood with respect to these mask tokens. And then we can use that gradient to compute a first order approximation to the change in log probability that would be produced by switching out the candidate prompt token with another token from the model's vocabulary. So the scores are kind of indicated by the darkness of the background in this matrix to the left. So once we've estimated this, we can then figure out the top K candidates for replacement, and then we can evaluate how well the prompts do on another batch of training data if we replace the mask with our candidate replacements. And so by doing this, this lets us know what the best replacement is. And so in the next iteration of this algorithm, we would then switch the mask token out with the best performing prompt token and then iterate until convergence. So carrying this process out, we would ultimately end up with something that might look like this. Okay, so how does this compare to manual prompting? So we looked at a couple examples in our data set. First, I'll go over SST2, sentiment analysis. And here we can see that there's a pretty substantial increase in the model's performance at sentiment analysis. And so this is cool because it's showing you that the model essentially is much better at detecting sentiment than you might detect if you had manually written prompts. And then since my work is mainly dealing with fact completion, the other key task we can look at is fact completion. So I discussed earlier that there's this llama benchmark, which had sort of formalized our evaluation approach from the Barack-Hillary paper. And so in this table, I'm comparing the prompts from llama with the prompts that were generated by autoprompt. And then I'm also showing the hits at one score to show you the difference in performance that we get from using auto prompts. And so one of the notable things is that it can be kind of hard to specify some relations in a way that provokes good performance from the language model. So highlighting here, we can see that for trying to predict the occupation of a person or the genre of a body of work, the original templates used in the llama dataset were not very effective. They would, you were getting less than 1% hits at one. Whereas when we go to whereas when we move to using auto prompts, we're able to get much better hits at one scores, although the prompts are, again, much more hard to, they're much less legible to humans. And this isn't to say that auto prompt always works better. So there are some instances where the original templates in the llama dataset actually are able to elicit better performance from the models than auto prompt. But again, if we sort of marginalize over all of these different relations, we can compare. And again, auto prompt was able to show that language models have substantially better fact completion capabilities than if you had used manually written prompts. And so to answer the question of how does auto prompt compare to manual prompts, it ends up that it's pretty good. Okay, and so this leads me to the last part of my talk, but maybe I'd like to break for questions really quickly, since this is a bit of a shift in focus.
So there's one question that came in a little earlier. I don't know if it's still relevant. It's more of a clarification, which said, how do you get a training set for the prompts? Are there a lot of ground truth sets available out there? Yeah.
So yeah, essentially, there are lots of data sets in NLP that try to test for specific aspects of knowledge of models. So as I had gone over earlier, like this glue benchmark, for instance, has a number of data sets, and each of those data sets tests one fundamental capability of an NLP model. And so because autoprompt really only requires defining a bunch of placeholders for the template, you can use essentially any data set to learn prompts. And so in auto prompt, for instance, we had used NLI data sets, we had used sentiment analysis data sets, and then we had used these fact completion benchmarks like llama.
Cool. Does anyone else have any questions before we continue?
Yeah, I was curious about the computational efficiency of auto prompt. It sort of seems like this search is a little tricky to do just because you sort of need to, from my understanding, sample a bunch of different trigger tokens. So I was just curious how long this takes to run with large language models.
So it generally does. It generally it generally takes about as long to run as like if you were to do fine tuning as a task with language
Really?
models.
Okay.
Yeah. So to maybe explain what's going on under the hood here, this loss back propagation is pretty much identical to what you would see during training of a language model, right?
Yeah.
And so then essentially what we're getting out of it is a gradient vector per trigger token. And so then in order to compute these candidate prompt tokens, we essentially take the inner product with that gradient vector with each of the token embeddings in the vocabulary. And so that is really roughly a it's pretty comparable in computational complexity to just predicting a word as an output from a language model.
Okay.
Yeah, so I mean, there's a couple, this iterative procedure, it's essentially extending the time per update step by an order of n, where n is the number of candidate prompt tokens you're considering. So the operations I've just gone over are like computationally similar in time complexity to doing language model training, but then that extra evaluation step where you evaluate the candidates can add a little bit of overhead, especially if you're considering hundreds of candidates. I think in practice, we found that you don't need to consider too many candidates, though. I think for SST2, we only considered 5, but it's been a while since I've checked the numbers in that paper. So all the details are laid out in the auto prompt paper if you're interested.
Thanks.
And while I'm here, I guess it's worth just noting that there's kind of a chicken and egg scenario that I didn't bring up, but here you've kind of got an auto prompt as the input to this automatic label token mapping step. And so in practice, what we ended up doing, I think, was that we initialized all of these placeholder tokens with mask tokens. But if you want to get better quality, you can kind of iterate between these label token detection steps and prompt template construction steps.
Cool. Any other questions? All right, we'll continue and leave the rest for the end.
Okay, cool. So now I'm going to make a little bit of a shift in topic, and I'm going to discuss some of the ongoing work that we have looking at prompts as an alternative to fine-tuning language models. And so there were a couple other experiments that we had run in the auto prompt paper that I haven't talked about yet, but one of them that we found pretty exciting was we actually compared the performance of auto prompt to actually fine-tuning models on SST2. And here we found rather astoundingly that if you took a Roberta model and just used auto prompt with it, you were able to get 91.4% accuracy on SST2. And so in comparison to Elmo, which would have been maybe the state-of-the-art approach roughly 2.5 years ago, we're actually getting what would have been state-of-the-art performance. And this is without having to train anything besides the inputs to the model and the tokens that we associate to the outputs. So we found this super exciting. And to explain sort of the reason why it's so exciting, I'd like to just quickly go over what I think is the biggest problem with fine-tuning nowadays. So with fine-tuning, essentially, we have this big pre-trained BERT set of model weights, which is maybe like a gigabyte in size. And then for every single task that we want to solve, we're going to have to train a new fine-tuned version of BERT. So if you're doing sentiment analysis, you're going to have a model for that. If you're doing question answering, you're going to have another model for that. And if you're doing reading comprehension, you're going to have another model for that. And so as you can imagine, if you are a research lab or a big tech company or anyone that's using these models for a downstream task, eventually your server's disk space is going to look like this. You're just overwhelmed with BERT checkpoints, and it's really become unmanageable. And so sort of compounding this issue is the fact that model parameter counts are getting out of hand. So I've discussed BERT here, but really there's been a lot of additional work scaling up these language models to larger and larger amounts of parameters. And so if we look back just a little over 2 years, maybe the original Elmo and GPT models had 100 million parameters, and then BERT has 300 million parameters. But now we're getting to a state where NVIDIA had published a model that has 8.3 billion parameters. And now with GPT-3 and TNLG, GPT-3 has got like a whopping 175 billion parameters. So it probably takes, I mean, I don't know the number off the top of my head, but you can imagine that this is like getting close to taking like hundreds of gigabytes or terabytes to store a single model checkpoint. And so going back to that issue of this like proliferation of BERT models, it's infeasible that you would be able to fine tune models like this to every task that you wanted to do. You know, even for the GLUE data set, which has just like maybe 10 tasks, that would be an absurd amount. But Samir had been talking about auto prompt with some other researchers the other week, and one of them sort of put its benefit quite nicely in that instead of having a billion parameters, auto prompt's really giving you a sequence classifier that you can write on the back of a napkin. Because all you need is this prompt template and some label tokens. So it's really just giving you a natural language input. And so inspired by this, we've really got an opportunity to really save space on people's hard disks and come up with a much more efficient solution for a wide variety of NLP problems by using auto prompt. And so that's really been what we've been investigating in our ongoing work. So we've been looking at evaluating prompts versus fine tuning. And we've been specifically focusing on few-shat tasks where there's maybe only 10 to 20 data points per label for your task. And the reason that we're focusing on that is that this is a setting where fine tuning has been shown to be particularly bad. So there's a lot of potential for auto prompts to be advancing the state of the art on these kinds of tasks. So in addition to just using the auto prompt approach that I just described, since we're starting to get more into a regime where we're interested in actually optimizing model performance, we're also going to look at a couple modifications that can allow you to slightly increase the parameter count of your model, but still nowhere near the billions of parameters or hundreds of millions of parameters used by BERT and Roberta and all of these big models. So I'm going to go over two modifications that we've come up with. One is called continuous prompts, and the other is called sandwiches. So continuous prompts, the idea is that we're going to use the same kind of input format as we did for auto prompt, but instead of trying to learn these placeholder tokens down here, we're instead just going to associate a word embedding to each of the placeholders, and we're going to optimize those directly. So that maybe is something that you can't write on the back of a napkin, but it is something where it's only it's like on the order of maybe thousands of parameters you're learning. So it's still orders of magnitude smaller than fine-tuning a whole BERT model. And then the extension to sandwiches is that we also will allow ourselves to train the projection weights when we're trying to predict words in the vocabulary. And so again, this is pretty lightweight, since for tasks where you have a fixed set of class labels, you essentially only have a very small finite number of words in your vocabulary that you're going to end up learning weights for. And so again, we're really only modifying a model's parameters by changes on the order of thousands of parameters, not millions or billions. Okay, and now this is just sort of the last part of my talk, where I'm just going to quickly go over some preliminary results we've seen on 4 of the data sets from GLUE. So here I've got 5 different models that we're comparing. First is this fine tuning being done in the traditional way with the class projection matrix that I had shown at the very beginning of this talk. Then I'm comparing the performance of discrete prompts, which is the method that we had covered in the auto prompt session, along with continuous prompts and the sandwich method. And then to provide sort of an upper bound on performance, I've also looked at what happens if you feed in a prompt, but then you fine tune the entire set of model weights. And to just distinguish that from the pure fine tuning approach, essentially the pure fine tuning approach is fine tuning on a classification objective, whereas this other method is fine tuning on a masked language modeling objective. And people have found that that's just more successful technique for this style of few-shot learning. And so here we see some really exciting results. So first of all, standard fine tuning just does not work very well on these problems. Whereas in contrast, we see a very consistent gain between discrete prompts going up to continuous prompts going up to our quote unquote sandwich architectures. And the sandwich in a lot of cases is getting comparable, if not better performance than a model where you've fine-tuned all of the hundreds of millions of weights in BERT or Roberta. And so here we've managed to show that by using a fraction of the parameters, we're actually able to get what I think is quite decent performance on these tasks. And so this is a very exciting development in this field of research, because we're now moving to a point where instead of having to store all these gigantic copies of models, we actually can just store really rather cheap inputs and still be able to deploy these models for a lot of different tasks. So yeah, our results are super promising so far. And before I end this talk, I just wanted to highlight that a lot of people have sort of made the similar conclusion to us. So these are all 3 papers that had been published on arXiv maybe in the last month. And it's just showing you that a lot of the NLP community is really focusing on this right now. It's become a very important problem to a lot of people. And hopefully we can make our mark on it before it becomes too saturated. And so with that, I'd like to conclude my talk. I'd like to thank all of my collaborators. There are a ton of people that were extremely influential in getting all of these things to work. And without them, I wouldn't be able to be here today. And I would also like to thank the agencies at the bottom for funding this research. And with that, I'd like to thank you all. If you're interested in more details on these papers, you can check them out at my GitHub website. And if you want to play around with auto prompt for yourself, we've tried to set it up to be extremely general in the kinds of tasks that you can use it for. So we really encourage you to try it out using the code I've linked here. And with that, I'd like to open it up for questions.
Thanks, Rob. Yes, if people have questions, feel free to unmute and ask. All right, maybe I'll ask one question while people are thinking about this. So are there certain styles of tasks where you think prompting could work better, and other tasks, like do you have any intuition for when this will work and when this wouldn't work?
So the easiest thing is that auto prompts work on tasks that are really like easy to frame in natural language, right? Sentiment is typically expressed often in text, so it's easy for it's kind of the poster child task that you can use this method on, because it's really easy to associate the positive label in sentiment analysis with words like good, fantastic, or great, and negative with bad, terrible, awful, or whatever. I think for tasks like NLI, it's definitely, they're more difficult just because it's very hard to map the problem into natural language. So saying that something's a contradiction, it doesn't, you usually don't see like 2 sentences that make no sense next to each other in language model training data, and then someone says, this contradicts this. So I think tasks like that, it becomes a lot harder to use auto prompt, although it still works okay. It's just we're not seeing state of the art performance compared to the case of sentiment analysis, where it was really kind of astounding how well the model did.
I see. Yeah, I guess the question is, yeah, that makes sense. It's not also clear what happens during fine tuning. So I guess I was wondering, are there cases where clearly fine tuning would just work, but prompting would just fail? And if we had to even think about artificially creating such scenarios, how would we even go about thinking, like, right? Anything that really differentiates these two styles of getting a model?
Yeah, I mean, it's hard to say because we're really like showing you the best case scenario for auto prompting with these few-shat examples, right? This case where fine tuning fails outright is kind of more symptomatic of having few to no training data points per like label, whereas when we start to look at comparisons of auto prompt to other techniques, auto prompt to fine tuning on full data sets, really the gap becomes quite substantial. So even for SST2, like the best Roberta performance, I think is like 96 or 97%. So even though we're feeling pretty good about getting 91%, that's a substantial gap. And if it's really driving, if the task is really important to people, I think they'd be willing to pay for more hard drives in order to get that 6-point gain.
And the benefits of prompt plus fine tuning, you imagine, will also go away at that point, or do you think?
I believe so. I would have to double check our results again, but I'm pretty sure that we've consistently seen that just once you get to the order of like thousands of examples in your data set, fine tuning really is a very hard paradigm to beat.
Okay.
Yeah, I guess the other answer to your question is that some tasks are really, really hard to map into this prompting framework. So we've really looked here at classification tasks with a fixed set of labels, or these fact completion tasks where you can just like sort of apply an identity mapping to get your label tokens. But there's a lot of other tasks where you might need to choose between two sentences, or the label sets might change from instance to instance. And on tasks like that, prompting has been shown to work, but I don't think it's been shown to be anywhere near as effective as some of the tasks that we've shown here.
Yeah, I guess it also goes beyond that, right? So like semantic parsing or coreference, like I have no idea how to think of those as prompting, but maybe I haven't.
Yeah. Or like squad style reading comprehension where you need to select a portion of a passage. Like that really becomes unwieldy when you're using prompts.
Right. All good ideas, good problems for future work.
Uh-huh.
Anybody else has any questions?
I had a question for Robbie. I may have missed this, but I think it was slide 76, the auto prompt prompts. I know you talked about it, so I probably missed it. They were very non-interpretable. Is it possible that there's some overfitting of some type going on here? Or, is this a warning sign of something, that it's solving the problem, but it's not really. So it's a very open-ended question, but I was curious.
Yeah, so I actually think that it's. I don't think that overfitting is a danger in this scenario, because the setup with how we've learned these prompts is that we've taken a bunch of to take, for example, occupation, right? There's a bunch of entities in Wikidata, and we're only taking a fraction of them. So it'd be something like Parrick Smith is a professor by profession, right? And so you see that during training, but that like it's kind of hard to use that to overfit to then if I say like Mick Jagger is a singer by profession, and that's what ends up appearing in the testing data. So I think these actually show you that you're actually getting very good generalization capabilities from the model. With that said, I think there's also, it's clearly amenable to exploiting statistical biases in your training data. So if we look at that occupation, you see the words like politicians and musician appear in the prompt. And so maybe that's guiding the model to pick words like politicians or musician, which are occupations of a large number of the entities in Wikidata. And to sort of extrapolate on that, we had done additional experiments on natural language inference in the auto prompt paper. And we had basically found that if there is class imbalance in your labels, auto prompt kind of defaults to always predicting the dominant class. So this is this method is very sensitive to cases where you don't have a lot of balance in your label distribution.
Thanks.
All right, anybody else? Okay, in that case, let's thank Robbie again. And yeah, thanks.
Thanks, everybody.